All right, so we're going to do 6.5 today, matrix inverses. So we can consider this system right here, okay? And we see our three different equations and what they equal. Earlier, we learned how to solve this system by rewriting it as an augmented equation. We can also create a matrix equation using the coefficient matrix A. So, of course, these are all the coefficients in front of the variables. The variable matrix, which is the order of our x, y, z, right? These are x's, y's, and z's. And then a constant matrix shown below. And then, of course, our constant matrix would be the answers to the equations. And what we need to do is find out what x, y, and z would make all of these true, right? So how would we solve this equation for the x matrix? We've never talked about matrix division. Instead, we can use the inverse matrix. Now, how can I connect that to make you remember? Well, in arithmetic, right, if I wanted to get rid of addition, I would subtract. If I wanted to get rid of subtraction, I would add. Multiplication, I would divide. Division, I would multiply. But as we just read, there is no matrix division, but we're still using the inverse, an inverse operation, okay? So we are going to find an inverse matrix that allows us to get our answer. So inverse matrix, what is it? Well, two n by n matrices A and B are called inverses if A times B or B times A equals I. Remember, the I is the identity matrix, which means all the diagonals are 1 and all the other elements are 0. If B is the inverse of A, we denote B as A to the negative 1, A inverse. That's how we see it. If A has an inverse, we refer to A as invertible. Now, we have to test both. So if we are to prove that these two are inverses of each other, we have to multiply one way and multiply the other way. Why do we do that? Well, because we know that multiplication is not commutative. You cannot assume one going A to B is the same as B to A. So we have to double check that. So let's do that now. Here we're going to try A times B. Okay, so I'm going to write that down. 1, 2, 3, 4. It looks like they made it easy on us. Okay, let's check our dimensions, because I want you guys to stay in that habit. So this is a 2 by 2 times a 2 by 2. Okay, that means that our ending matrix will be a 2 by 2. And let's see, row times the column. So 1 times negative 2 is negative 2. 2 times 3 halves is 3. And we add those together. And what do we get? We get the value of 1. Okay. Now let's do this element right here. So row 1, column 2. So 1 times 1 is 1. 2 times negative 1/2 is negative 1. When we add these two together, we get 0. Looks like so far so good. Okay, let's do 3 times negative 2 is negative 6. 4 times 3 halves is 6. Add those together, we get 0. Okay, last one. 3 times 1 is 3. 4 times negative 1/2 is negative 2. And then we get 1. And look, we have our identity matrix. We have the 1s in the diagonal and the 0s everywhere else. And of course, to be an inverse, you have to have it both ways. So now let's test BA. So we have negative 2, 3 halves, 1, negative 1/2 times this 1, 2, 3, and 4. All right, so let's do that again. We know it's a 2 by 2, so we know here. Now, negative 2 times 1 is negative 2. Negative 2 times 3, did I write something? Oh, negative 1 times 3 is 3, so we get that value of 1 again. Negative 2 times 2 is negative 4. 1 times 4 is 4. Add those together, we get 0. 3/2 times 1 is 3/2. Negative 1/2 times 3 is a negative 3/2. Put that together, we get 0. 3/2 times 2 is 3. And then negative 1/2 times 4 is negative 2. And we get that 1. And what do you know? Again, the identity matrix. So that means that, yes, they are inverses of each other. All right, we can use the matrix operations and reduce row echelon form to find an inverse. Matrices without inverses are called singular. Matrices that have inverses are referred to as non-singular, by itself or something with another. So, finding the inverse of an n by n matrix A. Form the augmented matrix. So we're going to do our augmented matrix, and then we're going to have our identity matrix right next to it. Then we're going to use our row operations to switch the two. So we're going to move our identity matrix over here. We're going to make it so this augmented becomes the identity. Once we get the identity on the left side, whatever matrix is on the right side would be our inverse, okay? So we're going to do that here with matrix A. So I have matrix A on this left side. So 1, negative 2, 2, negative 3. I'm going to put my line down here and put the identity matrix of a 2 by 2. Now I'm going to use my row operations to be able to move, to make this look 1, 0, 0, 1. Remember, when we learned this before, we always start right here and we go down here and around, so counterclockwise. So I like it that this already has 1. So now what we're going to do is say row 2 minus 2 row 1, because that will give us 0 right here. Okay, when we do that, what happens is we end up with 0, 1, negative 2, 1. Yes, I did not perform the operations right now because we've practiced this before, so we should be okay with it on the side, and I'm just showing you. Then what we will do is we have our 0 or 1 here, and now we want 2, so we're going to have our row 1 plus 2 row 2, because that makes that 0 then right down there. What we end up getting is 1, 0, negative 3, 2, 0, 1, negative 2, 1. So what does this mean? This means that the inverse of matrix A equals negative 3, 2, negative 2, 1. And of course, we could prove that by multiplying those two out. If we're able to multiply those two out, then they should give us the identity, okay? Now, given a 2 by 2 matrix, find the inverse if it exists. So this is just us doing it again. just to test it out if it's actually working. So let's see what happens. So 3, 6, 1, 2, and then our identity. All right, so first thing I'm going to do is I'm going to switch row 1 and row 2 because I like that one, but I like it up there. All right, so 1, 2, 0, 1, 3, 6, 1, 0. Sorry guys, my pencil. Now what we can do is I want to say row 2 minus 3 times row 1. And what do we end up with is 1, 2, 0, 1, 0, 0, 1, negative 3. All right, because we cannot get the identity matrix right here because it's already 0. Sorry guys, I didn't see that wasn't on the screen. Because it's 0, 0, it can't be the identity matrix. That means no inverse exists. Okay. All right. Say we had the matrix A equals A, B, C, D. What we find out, guys, is that you can find if there's or get the identity, not the identity, the inverse matrices just by doing a formula. Some of you might remember this from secondary 1, but if you don't, this is what happens. What we need to do is to get the inverse, it's 1 over A times D minus B times C. Okay, and then we have to switch A and D and make B and C opposite to what they were up here. Okay, once you have that though, you then have to multiply that scalar in. I'm going to prove that to you right now. Let's do, we know example 2 had inverse, so I'm going to show you right now. If I said A equals 1, negative 2, 2, negative 3. Okay, instead of doing the row reduction stuff, I'm actually going to do this. The inverse equals 1 over A times D. So that's 1 times negative 3 minus negative 2 times 2. Then we have this matrix. I switch A and D and make B and C opposite. I don't switch them. I make them opposite. They just happen to look like they switch. Okay, so be careful with that. Now, if I continued this, I would have 1 over, let's see, that is negative 4, positive 4, negative 1, and positive 4 is 1. So luckily, look at this. I didn't even have to do that scalar multiplication because anything times 1 is itself. And what do you know? We see this is an example 2 right over here, that they are the same ones. Okay? So if it's a 2 by 2, we actually have a formula that we can use to get the inverse. However, the only thing it works with. So if we have a 3 by 3, we have to do the row reduction, okay? So let's do it. Let's test it out. All right. 2, 3, 2, 3, 3, 4, 1, 1, 1. Draw our line, draw our identity. So 1, 0, 0, 0, 1, 0, 0, 0, 1. All right, what can we do next? Well, if I need 1 over here, one of the things I can do is just take row 1 and multiply it by 1/2. So I get 1 3/2, 1/2, 1/2, 0, 0, 3, and fill the rest of these out. 1, 0. All right, what can we do next? What are we going to do next in the next one here? So I want to make this 0, right? So looks like I am going to take row 2 and subtract it from 3 of row 1. Okay? Sorry, guys. All right. What I end up getting is 1 3/2, 1/2, 1/2, 0, 0. In the middle row here, I get 0, negative 3/2, negative 1/2, negative 3/2, 1, 0. And then, of course, this bottom one stayed the same. Oh my goodness, it's running out. Sorry, guys. Here we go. 2, 4, 1, 0, 0, 1. Okay, what would be my next one? Well, I need to get a 0 down here, right? So I would have row 3 minus 2 of row 1. Right, what does that give me? Of course I did that, huh? 1 3/2, 1/2, 1/2, 0, 0, 0, negative 3/2, negative 1/2, negative 3/2, 1, 0. And of course my third row is what I was messing with, right? I get 0, 1, 0, negative 1, 0, 1. All right, now what? You know what I like? I like that third row, but I wish it was in row 2. So why don't I do that? Switch, switch, row 2 and row 3. Now remember, I like that because I want the 1 in the middle. 1 3/2, 1/2, 1/2, 0, 0. I'm going to switch it, right? So 0, 1, 0, negative 1, 0, 1, 0, negative 3/2, 1/2, negative 3/2, 1, 0. Looks good. Okay. Now what do I need? I need a 0 right here. So what does that mean we can do? Well, we can take row 3 and add row 1 to it. It's a lot of space, huh, guys? First row stays the same. Negative 1, 0, 1. Okay, so that third row, what that changes to is 0, 0. Now, what is it? I'm trying to think, guys. Oh, this is why I can't do that. Because if I add row 3 and row 1, what happens to this right here? It becomes a 1. So I actually can't add it to row 1. What I have to do is add it to 3/2 row 2. And that is where I come into this 0 here. Does everyone understand? I'm going to say that again. I could not add it to row 3 because if I added it row 3 and row 1, I would now have a 1 in the spot, but I don't want a 1 in the spot. I like the 0 in that spot. So what happens is when I have row 3 plus 3/2 of row 2, I end up with 0, 0, negative 1/2, negative 3, 1, 3/2. All right, remember, once I do that, I got to go up. So next thing I'm going to do here is multiply row 3, because I need this to be a positive 1. So I'm going to multiply it by a negative 2. I'm running out of room, everyone. 1 3/2, 1/2, 1/2, 0, 0, 0, 1, 0, negative 1, 0, 1. Let's multiply everything by negative 2 here. So 0, 0, 1, 3. Oh, by negative 2, so negative, positive 6, right? Negative 2, negative 3. All right, I like this so far. Now I got to come back up here, right? So next I'm going to get rid of this 3/2 and make it a 0. I can make it a 0 by saying row 1 minus 3/2 row 2. Gosh, I'm running in a room. So what I'm actually going to do is go on to another sheet of paper and continue my matrix here. So when I do that, I get 1, 0, 1/2, 2, 0, negative 3/2. All of this stays the same. Okay. One last thing is that 1/2. So I'm going to take row 1 because that's what I want to change, minus 1/2 of row 3. Okay. When I get that, I end up with the identity matrix on this side. I end up with negative 1, 1, 0, negative 1, 0, 1. There we go. So that means my final answer is that the inverse of matrix A is negative 1, 1, 0, negative 1, 0, 1, 6, negative 2, negative 3. All right. Now, here's where most of you will not take this opportunity. But really, if this was a final, I would multiply matrix A in the inverse way and make sure it comes out with the identity. That's how you know you have a right answer. All right. Excuse me. So here we go. Now we're going to actually use this idea of the inverse matrix to solve for our unknowns here, okay? We have to use we want to use the inverse matrix if we are given one, okay? For the fact that if we have our augmented, which is 3, 8, 4, 11, and we multiply it by our x, y, our variable, we need to get 5, 7, which is our solution. So keep this in mind. This is very important up here. I just set this up as matrix A times matrix X equals matrix B. So again, we're solving for X. Now, if this were a normal algebra problem, you would say, well, let's divide by A. But of course, there's no division in matrices. So how do you get rid of A? Well, we want to make it the value of 1, which is the identity. The way to do that is to multiply it by its inverse. But we've learned through algebra that whatever we do to one side, we have to do it to the other to be able to keep everything balanced. Here's the tricky part. Remember that multiplication order matters for matrices. So you see how I'm multiplying the inverse in front? It also means that I have to multiply the inverse in front. Okay? This is how I will find what our variable matrix is. Well, to do that though, I need the inverse first. Now, this is our 2 by 2, so let's do our little trick. The inverse of A is going to be 1 over A times C minus B times D. And then remember what we do. We switch A and C, and we do the opposite for B. Opposite. Oh, did I do that? I've been saying C, haven't I? It's A times D minus B times C. Switch A and D and make B and C opposite. I was saying the wrong variable. Right spot, wrong variable. Okay, so when I do that and I actually bring that down, I find out that this is 33 minus 32, which is 1. Isn't that nice that that came out correct? So our inverse, or to 1, so our inverse is 11, negative 8, negative 4, 3. Okay, we found our inverse. So now we are going to solve for X by saying that X equals the inverse of A times the matrix B. So let's do that. So our XY matrix equals 11, negative 8, negative 4, 3. That's our inverse. Times our constant matrix, which is 5 and 7. What do you know? There's our multiplication. And when we do out our multiplication, I'm going to do this quickly because we should have done enough. We come out that our X, Y matrix equals negative 1, 1. Now, in mathematics, we always want a way to check our answer. We can do that by plugging in negative 1 for X, 1 for Y, and making sure that equals. If I plug in negative 1 for X, 1 for Y, do I get 5? Yes. If I plug in negative 1 for X, 1 for Y, do I get 7? Yep. So this is finding the solution by using matrix inverses. Other thing I want to point out as we move on is if your question ever says solve by this certain way, you must solve by this certain way. Now, what I want you guys to see right here is realize that this matrix, our A matrix, right? Our A matrix, which is 2, 3, 1, 3, 3, 1, should look familiar because we did this earlier. We did this earlier and we found that the inverse was negative 1, 1, 0, negative 1, 0, 1, 6, negative 2, and 3. So negative 3. So when we have the inverse, luckily, because we did all that work for it already, we can automatically set up that x equals the inverse times our constant, right? Now here's the thing. That means our variable x, y, z matrix equals this 2, 3, 1, 3, 3, 1, 2, 4, 1. And then we're going to multiply it by our constant, which is our 4, 2, 5. If you want to practice your multiplication right now, what I would do is pause the video, do out your multiplication, and see if you come up with the same answer that I do. Okay? So when I do the multiplication, what happens is we get -2, 1, and 5. Well, what does that mean? And sometimes, depending on the question, they want you to write it in a quarter and pair. So the solution to this is -2, 1, 5. And then we can do the same thing down below. We know that we have our variable matrix equals our inverse matrix. Now, guys, yes, I am going along with this, and guess what I just did? You guys see what I just did? I'm hoping that when you pause the video and you came back, you realize, heck, man, you did this wrong because I didn't get that answer. I didn't use the inverse matrix, guys. Did everybody notice that? Luckily, I did all this work ahead of time to have the right answer, but I wrote down the wrong matrix. Okay, so this is the inverse matrix that you are supposed to multiply by the constant matrix. There we go. And now you get -215. Okay, so down here again, I've got to use that inverse matrix. -1, 0, 1, 6, -2, -3. Okay, by the way, I knew to use this inverse because look, the A is still the same. The only difference is that the constant matrix is now 11, -2, and 15. So multiply that out. Take a moment if you want to do it by yourself. All right. And the answer we get is -13 for 25. So again, if it wants it in a coordinate pair, I would do this as -13, 4, 25. Awesome.